So today we'll be finishing this topic. So let us solve few questions based on this area, what we studied in the last class. So let us read this question. This very simple. See, questions from fluid machinery. I already told you. Now will be very simple. Just few basic things and we are done. Let us read this question. What it says that there is a vertical shaft Francis turbine. Mind the word vertical shaft. Okay. Francis turbine rotates at 300 rpm. It says that the available head at the inlet to the turbine is 200 meter. Okay, and then it says that the tip speed of the rotor is 40 meter per second. Okay, and then it says that the water leaves the runner of the turbine without wall. That means what it says that VW2 value is 0. Okay, and we have seen that in Francis turbine VW2 was 0. So see the idealization and the questions are matching. And then it says that the velocity at the exit of the draft tube is 3.5 meter per second. At the exit of the draft tube, mind the word again, exit of the draft tube. Okay, the screen is not shared, sorry. Yeah, good afternoon. Now screen is shared, right? So okay, let us quickly read this question again. What it says that there is a vertical shaft Francis turbine which is rotating at 300 rpm, and then it says that 300 rpm, it says that the available head at the inlet to the turbine is 200 meter, and then it says that the tip speed of the rotor is 40 meter per second. Then it says water leaves the runner of the turbine without whirl. Without whirl, what do we mean? That VW2 is 0. Okay, then it says velocity at the exit of the draft tube is 3.5 meter per second. Velocity at the exit. So if we term V1, V2, then which value is given to us? V3. We have seen now that exit of the draft tube, we saw that the velocity was V3. Then it says that the head losses in different components of the turbine are in the stator part and the guide vanes, it is losing 5 meter. Then in the rotor, it has lost 10 meter head losses, mind the word. And in the draft tube, it is losing 2 meter. And then it says that the flow rate through the turbine is 20 meter cube per second, and take G 9.8. Then it says that the hydraulic efficiency of the turbine. So what is hydraulic efficiency? Let us quickly recall that. What was hydraulic efficiency? Can you recall what is hydraulic efficiency? This was the ratio of what is the head developed by the turbine divided by what? Divided by what is the head available. Yes or no? What was the hydraulic efficiency? Power delivered, or head in terms of head we can calculate it, means the hydraulic efficiency in terms of head is that what is the head developed by turbine, head developed by turbine divided by what was the head available to the turbine. So what is the head available? This is directly given to us is 200 meter, right? 200 meter, this is given. So how to find out what is the head developed? So head developed to the turbine, how do we find it? Let us find head developed. Okay. So can you see that head developed will be, let me call it here. So before that, you mind this formula, or not formula, means the equality thing, is that H at the inlet, this will go to whom? This will go to, from this part, there will be some head which will be developed by turbine. Yes or no? Turbine. And some of this will go into head loss in the stator, and some of this will go into head loss into the guide vanes, HL in the guide vanes. and then some of this will go into what? Head loss in the rotor, head loss in the rotor, and some of this will go into what? Head loss into draft tube, plus there will be some velocity at the exit of the draft tube, right? So how to convert velocity into the head is, we know this fact that v square upon 2g, and moreover this is v3. So head at the inlet is 200 given to us. Okay, head developed by turbine, we need to find out what is the head developed by turbine. And head loss in stator plus guide vanes is given as, stator plus guide vanes is given as 5 meter. So this is 5, this is 5, and plus head loss in the rotor, head loss in the rotor is given as 10, plus head loss in the draft is given as 2, and V3 is given as 3.5. So 3.5 whole square by 2g. So you take the sum of these two, take the difference, then you will get the what is the head developed by turbine. So head developed by turbine, this is equal to 200 minus 5 minus 10 minus 2 minus 3.5 whole square divided by 2g. So this value is equal to 182.375 meter. So what is the hydraulic efficiency now? Neta hydraulic, this will be equal to head by turbine divided by what was the head at the inlet, and head at developed by turbine is 182.375, and head at inlet is 200. So the ratio of these two will be somewhere around 0.999118. So this is 91.18%. See, simple na. There is no, means even someone is aware of the fact that how to calculate, means what is the hydraulic efficiency formula. Even if he is not aware of the very deeper insights of hydraulics, he's still able to do just the basics. I told you now that gate is never going to check you that if you are very pro in calculation, but they will check you that if you can put some analogy into it. Okay, so they will check this part, always. Okay, let us move to the next question. Let us read this question first. Read this question. It says that for a Kaplan turbine, the outlet blade velocity diagram at a section is given. Kaplan turbine means what? Axial flow, right? Axial flow turbine. The outlet blade velocity diagram at a section is given. Outlet velocity diagram is given. Okay. Then it says that the CF is, this is flow velocity, and then it says that this is blade velocity, and then this is relative velocity. Okay, then it says that the diameter at this section is 3 meter. It means that it is drawn at which diameter? The diameter at this section means we have seen now that there was a hub, upon which we have seen there where the hub part we have seen, right? And on this hub we have blades on this hub. Okay, so on this hub we have blades. So this says that this is the diameter at the section where diameter is 3 meter. Okay, the hub and tip diameters of the blade are 2 meter and 4 meter. That means this we knew that this is hub diameter dh, this is 2 meter, and this is given as 4 meter. Okay, then it says that the water flow rate, volume flow rate is 100 meter cube per second. That means Q value is directly given 100 meter cube per second. Then it asks you the rotational speed of the turbine is 300 rpm. That means N value is also given to us is 300 rpm. And then it says that the blade outlet angle beta, this is what? That means this angle they are asking about. For this angle, at least I need two of these value. two of these value, then only I will be able to find. So let us see that which value we can easily reach. Okay. So CB is blade velocity. This we can easily find out. CB is pi dn by 60. Yes. And what is pi? Pi is anyway pi only. And d is 3 meter. This is given as that the hub, this is 3 meter. So this is 3. And n value is given as 300. RPM means revolution per minute divided by 60. So this value will be in meter per second. Okay. So this is equal to 47.12 meter per second. So CB, this is nothing but U only. What they have tried to do here is that they have used different notation so that you get confused that which one is denoting whom. Why? Because we people usually keep in mind those notations which we have studied in the classroom or in the books. So they have just tried to deflect you on that fact, but this is nothing to be worried. So I knew that okay, this is U, and this value is now known. This is 47.12 meter per second. Okay. Do we remember that Q value in the Kaplan turbine? We denoted that this was nothing but area into velocity of flow. And what was this area of the flow? AF. This was pi by 4 into DO square, means outer tip diameter square, minus diameter of what? Hub and tip. So diameter of hub whole square. So into VF. So Q value is anyway given to us, not directly 100 meter cube per second. So this is 100 Q meter per second. So do we know that this is 100? This is equal to pi by 4 into D outer is 4. So 4 whole square minus DH hub diameter is 2. So 2 square multiplied by VF. VF anyway we need to find. So what is this value? VF is equal to 400 divided by pi into what? 16 minus 4, 12. So VF value is somewhere around 10.61. So this value is what? VF2. Okay. VF2. VF2. And this VF2 is nothing but given as CF. So now I will notate that okay, CF is given as 10.61. So now I know CF. Now I know CB. So can we use tan of this angle? Tan beta, tan beta, tan beta, this is equal to tan beta is equal to what? CF upon CB. So CF is anyway 10.61 divided by 47.12. So this value will get you the beta, and from this one we'll get that beta is equal to 12.7 degree. Simple. Tell me you are able to follow, or I am the one who is writing and you are just mute spectator. Means what we have done in class. Yeah, you are solving parallelly. Very good. Just what we have done in the classroom, the same thing is appearing in the exam. So do we appreciate that also? That everything what we have studied now in that form only questions will appear, but you will have to think after that how to put the analogy between what you know and what is given to you. See. Okay. Next, let us solve next question is here. Read this question. Could I give you 2, 3, 4, 5 minutes to solve this question? This is very good question, appeared in the GATE exam only. Okay. See, the blade and fluid velocities for an axial turbine, mind the word axial turbine, are given as on. Okay. It says that the magnitude of absolute velocity at entry is 300 meter per second at an angle of 65 degree. So I know that this is v1, nothing but v1. This one I know. At an angle 65 degree to the axial direction. So what is that axial direction? This is now axial direction. Mind the word direction. This is very important that it has mentioned that axial direction is this one. Okay. While the magnitude of the absolute velocity at the exit is 150 meter per second. So this I know that this value 150 meter per second, this is v2. Why? Because it has mentioned absolute velocity, absolute. So that is why I am writing this one as v1 and this one as v2. Then it says that the exit velocity vector has a component in the downward direction. There is one component in the downward direction at the exit velocity. Okay. Then it says that given that axial velocity is same at the entry and exit, the specific work means it has also mentioned that axial velocity axial velocity. And how did we denoted it? As vf1. And it says that vf1 is vf2, and this anyway we have appreciated also in the axial turbines vf1 was vf2, so this has been mentioned. So now your job is to find out a specific work. And how do we find out the specific work? This is rho times q into vw1 u1 plus vw2 u2. This is how we will do. Okay. Hmm? Yes. And it has mentioned that the blade speed is 150 meter per second. So it must be mentioning the average velocity. In We have hub diameter and we have outer diameter, so the average of these two were used to calculate u. If you remember, then I told that u is u1 is equal to u2, right? So now u, this is done. There's no nothing to be worried about you. What about vw1 and vw2? Why? Because we need to find out vw1 and vw2. So I am removing the ink part. Now see, what is vw1 and vw2? The direction of vw1 and vw2, this is very important. See what it has mentioned, 65 degree to the axial direction. That means the axis of the blade is like this one. So this is the axial velocity direction. So that means this is now denoting vf1. Earlier what we are means what we have followed usually, that this is vw1, right? vw1. But initially the blade was like this one, then vw1 was this. But now the blade has been shaped like this, so therefore the axis is in this direction and vw1 will be perpendicular to it. So now my vw1 job is done. Vw1 is nothing but 300 sine 65. Vw1 is 300 sine 65. Okay. So vw1 is done. This is 300 sine 65. Okay. Now my job is to find out what is the exit at the exit. So vw2 I don't know, but some hint is given to us that vf1 is equal to vf2. My job is done now. Vf1 value I know, that 300 sine 65. This will be equal to what? Let us say that this is the angle between these two. So let us say that this is theta. So this is equal to what? 150 cos theta. No, no, sorry. Vf1 is 300 cos 65, right? Vf1 is 300 cos 65. This is equal to 100 cos theta. 100 cos theta. So from here, what we are able to do is find out theta. And what is that value? Theta will be 32.3. This will turn out as 32.30 degree. So now I can find out what is the value of VW2. So VW2 is in this direction, and VW2 value is 150 multiplied by whom? This was cos, so this is sine 32.30. Okay. So VW2 value is 150 into sine 32. So solve these two, and now you can find out what is the specific work done. W is, rho is given to us is 1000, Q is mentioned. If it is not mentioned, we'll convert it into per unit. So U is not mentioned, right? So U will consider, sorry, Q we will consider as per unit, and let us take out U also common. U is given as 150 meter per second multiplied by, what was there? We have 300 sine 65 VW1, and minus of minus, so let us make it plus. Why? Because the VW1 and VW2 are in opposite direction. So this is 150 sine 32.30. So this will now give you the value of work done. And what is this value? Can you tell me? Is there any doubt, Anand? Quickly tell me, is there any doubt? Please tell me, are you listening to me? What happened? Should I continue? Okay, let me continue. So from here, your W value will be 52.80 kilojoule per kg. Okay. Okay. Moving to the next part of this topic. We have no more questions to solve now. Okay, now. So now let us understand one very important. Okay, how I took 100 cos theta. Which one? Where? Oh, this is 150. This is 150. I'm sorry. This is 150. No, this is 150. Not 100, 150. Mistakenly, I have written 100. This is 150. Got it? Yeah. Okay. Now let us move to very important. If you haven't seen this, just watch this, that how I have written. So it is just good practice that at one place you are writing all of the things. Okay. So in these forms, questions will keep on appearing in the exam, that they will mention you few things, they will be asking you few things. So you should mind that what is given to you and how do you utilize the given information, because utilization of the given information, I have told you now that in the applications part there will be datas only, and you have to play with them, that how to find out the unknown thing. So the relation correlation between them you should know. Okay, now let us understand unit quantities. See, what is unit quantities? It is the parameter. It is the parameter. It is the parameter which is calculated. Means what I will do, that if turbine is working under unit head, then what is discharge? If turbine is working under unit head, what is the speed? If turbine is working under unit head, then tell me what is the power. got the idea that what is unit quantity is that I will make the turbine work under unit quantity of that. Maybe let us say that I'm talking about head, maybe I'm working under unit speed, maybe I am working under unit discharge, maybe I am working under unit power. Then what other quantities, how they will follow, this is my idea to do this uh, topic, right? So unit quantity is, it is the parameter, it is the parameter of turbine. Got the idea? It is the parameter of turbine which are calculated by, which are calculated by, calculated turbine by turbine under unit head. Okay. So during the calculation, what do we do is that the overall efficiency is remain constant. Okay, and we used to compare the performance of same turbine working under different operating conditions. See, what happens is that you know one operating condition, and you know that at this condition I am having certain power, certain discharge, certain speed, and other things. So when you will change those quantities, like if you are not working at, like let us say you were working at 100 meter, right, 100 meter of it, but now let us say that you have moved to 300 meter, then how other things will follow, this is the idea to do unit quantities. Okay, so one thing which will be fixed, that the efficiencies parts are not touched, means the overall efficiency has to remain constant. So during the calculation, what I have assumed is that, we have assumed is that neta overall remains constant. This remains constant, and this is used to compare the performance of, used to compare used to compare used to compare the performance of, the performance of performance of of same turbine, of same turbine same turbine under different operating conditions, same turbine under different operating conditions, under different operating conditions. Okay, so let us first understand what is unit speed. Unit speed, unit speed means nu. Okay, so what is unit speed? What will be the speed of turbine when I am working under unit head? So this is speed of turbine, speed of turbine under unit head. Okay, and similarly, what is unit discharge? Unit discharge q, this is discharge from turbine under unit head. Discharge from turbine, from turbine under unit head, under unit head. Okay, similarly we have unit power. Unit power, unit power is pu, this is called qu. Unit power is called pu. This is equal to shaft power developed by turbine, shaft power, shaft power developed by turbine, developed by turbine under unit head, under unit head. Okay, so let us first find out what is how to find out nu. Okay, so u, where we can see n we have seen is this is appearing into u formula, that u is pi d n by 60, right? Here we can see u. So can we see that u is directly proportional to d times n? Okay, so can I say that u is also directly proportional to n? And we know one more thing is that u, this will be proportional to velocity. Why? Because if the velocity is high, the velocity of the rotor, this will be also high. So this is nothing but the rotor velocity, right? So if v is high, u is also high, so u and v are directly proportional. And we have seen what this was, root over 2gh. So v is directly proportional to the square root of h. So can I say that u is directly proportional to v, and v is directly proportional to the square root of h? So can I say that u is also proportional to the square root of h? Okay, and we have seen that u is directly proportional to n also. So can I say now that n is directly proportional to the square root of h? So can I say now that n upon root over h, n upon root over h, this will be some constant, this will be some constant. Yes. Okay, so and unit speed, what we need to find out is unit speed. So what I can do is that nu upon root over h, u is equal to n upon root h. Why? Because I have said that n upon root h, this will have to remain constant. So whatever is the n, whatever is the h, the ratio of these two will remain constant. And hu, we have already seen that what is unit speed. Unit speed is the speed of turbine working under unit head. So by definition, what we can say that hu is equal to 1. So can I say now that my unit speed is nothing but n upon square root of h? Tell me you got it or not. Nu is n upon square root of h. Got it? Tell me. Okay. Simple na. See, things are very simple here. Just we need to break out that whatever we can see, let us break it out so that there is nothing hidden. Okay. So Nu is non now. So Nu is n upon root h, and moreover n upon square root of h of 1 is equal to n upon square root of h at 2. Okay, now let us find out unit discharge. Unit discharge. Unit discharge. So how we will find out unit discharge? Q is area times velocity, right? And how do we break this area? Area is pi by 4 into d square. Yes, and this multiplied by velocity. Okay, so can I summarize that q is directly proportional to d square into v? And can I summarize that q is directly proportional to v? Yes. And we have seen that v is directly proportional to the square root of h. So can I say that q is directly proportional to the square root of h? So in order to convert it into unit quantities, again what I can say that q upon square root of h, this has to remain constant. Okay. So can I say now that q upon root over qu upon root over hu is q upon square root of h? So can I say now that again by definition hu is equal to 1. So can I say now that qu is q upon square root of h? Okay, and moreover I can say that q upon square root of h at 1, this condition has to be maintained, that q of square root of h at 2. Why I am writing like this means q1 upon square root of h1 is equal to q2 upon square root of h2. Okay, third. Unit power. Unit discharge we knew. Now unit power. This is not unit means power is unity. No, the what will be the power when your head is unity? Okay, so power we know soft power. This is rho g q h, not soft power. Um, uh, Water power and multiplied by overall efficiency will give you soft power. Okay, so can I say now that power developed is directly proportional to whom? Q into h. Q into h, and power developed is directly proportional to Q into h, and Q just now we have seen this was directly proportional to the square root of h. Somewhere we have seen here Q is directly proportional to the square root of h. So let us put that Q is square root of h into h. So can I say now that P is directly proportional to the h to the power 3 by 2? So can I say now that P upon h to the power 3 by 2, this has to remain constant? So again, unit power, that means Pu upon Hu to the power 3 by 2 is equal to P upon h to the power 3 by 2. So can I say now that what is unit power? Pu is equal to P upon h to the power 3 by 2. Okay. So can you see that nu is directly proportional to the square root of h? Qu is also directly proportional to the square root of h, but Pu is proportional to what? H to the power 3 by 2. Okay. Got the idea? Tell me quickly. Okay. Let us moving to the next part. Okay. Now let us understand what is specific speed. Specific speed. So what is this? It is the speed of the geometrically similar turbine. I'm writing down here. It is the see. We need to compare the turbine at different operating conditions. Okay, this is very important part of the turbine analysis. So what is specific speed? It is the speed of the geometrically similar. Geometrical similar, we have, you must have done the in the dimensional analysis, model and prototype analysis, you must have done that geometrically similarity, what is kinematic similarity, what is dynamic similarity. Do you know these facts? Do you know what is geometrical similarity and all? Tell me. Yes, okay. Somebody says yes. See, this is nothing but that if your what is geometrical similarity? Let us say that one body, a body has diameter of 10 mm. Okay, and you have applied it to 100 mm. So what is that? That there is one scale ratio. So when we are saying geometrical similarity, then the corresponding dimensions should have the same ratio. Means that if you are taking the length ratio, so length of the let us say model and prototype, so this length ratio, width ratio, these things should be remaining constant. Got the idea? Then I can say that this is geometrically similar. Geometrically similar means what? That see your model, or let us say that there are two turbines. So one turbine has some, let us say, some length, width, and diameter. And similarly, another turbine has some length, width, and diameter. So the ratio of corresponding lengths, corresponding widths, and corresponding diameters, these three are, if they are constant, then I can say that this is geometrically similar. Okay. So now, if what is a specific speed, it is the speed of geometrically similar turbine. That means that the shapes are identical, winds angle and other things are also equal, which will produce unit power when working under unit speed, sorry, unit head. So what is a specific speed? That if the turbine is to make work unit head head under unit head, then it will produce what? Unit power. If I am working under unit head, then, sorry, if I am working under unit head, that means head is equal to 1 meter, then what is the power I am developing, and at what speed? So this is the speed which is called specific speed. This is called specific speed. Got the idea? What is specific speed? This is the speed, at which there will be unit power developed under unit working head. Under unit working head, if you are able to develop unit power, then there will be some corresponding speed, and that speed is nothing but specific speed. So it is used to compare. What is the job of this? It is used to compare the performance of different turbine irrespective of their sizes. Why? Because we have applied on geometrical similarity basis. So there is no need that they are what they are of same size, but we can apply. So if I know the specific speed, like what is the specific speed, then I can compare that, okay, this turbine needs this much speed to under unit head to produce unit power, the other turbine is required to work at this speed when it is working under unit head to generate unit power. Got the idea? So let us find out that what is the expression for specific speed. What is the expression for specific speed? Specific speed. So shaft power, we know that this is overall efficiency, multiplied by rho g q h. This we know. Okay. So can I say that power is again proportional to q into h? And q we have seen is directly proportional to d square into n. Why? Because area into velocity, area is d square, and v is directly proportional to u, so this is proportional to n also. Okay, so q is directly proportional to dn, and u is proportional to what? Dn. This we also know that u is pi dn, so from that u is proportional to dn. So can I say this? We know now that u is proportional to v. So now can I say that v is directly proportional to the square root of h? So square root of h is directly proportional to dn. Square root of h is directly proportional to dn. So can I say that d is directly proportional to square root of h upon n? Okay. So d is square root of h upon n. So now let us put these things into q. So q is now directly proportional to square root of h by n whole square multiplied by n. And n is what? N is again proportional to root h, we have seen. So n is proportional to root h. So q thing is done. So now can I say that power is directly proportional to qh? So power is now what? Power is directly proportional to square root of h by n whole square into square root of h into h. So let us solve this one. So now can I say that P into, this is H, this is H to the power n square into H to the power 3 by 2. So can I say now that P is proportional to H to the power 3 by 2 plus 1 H to the power 5 by 2, right? Upon n square. So can I write down now that n square into n square into P divided by H to the power 5 by 2, this is some constant. This is some constant. This is none. And by definition of a specific speed, what we assume that power, by definition of a specific speed, by definition of a specific speed, by definition of a specific speed, we have seen that that power is equal to 1 kilowatt and n is ns when your h is equal to 1 meter. So let us put these things here. So can I put that n square into p upon h to the power 5 by 2 is equal to, this is constant now, so now I am putting those things at a specific. So n is ns, so ns square into p upon what, ns square into p upon what we have, h to the power 5 by 2. So we know that p is 1 and this is also 1, so 1 to the power 5 by 2 is anyway 1, this is also 1. So I am writing down here that ns, can I see now that ns is nothing but n, ns square, ns square is n square p upon h to the power 5 by 2. So can I write down this one as ns is n root of p divided by h to the power 5 by 4. Can I write this? ns is n root p divided by h to the power 5 by 4. Okay. Now let us so if any turbine is working under any different conditions, their specific speed has to remain same. Means ns, why? Because ns is n root p upon h to the power 4. So the specific speed of a turbine is fixed. Okay, so a specific speed of a turbine under any operating conditions, this is not going to change. Means that there are three values n, p and h. So the changes will be in these quantities, but the specific speed has to remain constant. So if you have to compare the turbine at two different working conditions, few things are given to you. So what you will compare, their specific speed is to remain what, constant. Okay, so let us now understand model and prototype relationship. Model model and prototype type relationship. Model and prototype relationship. So how do we do is that, one, we have tangential velocity of wheel. Tangential velocity of wheel. We understand what is model and prototype now. So what we will do is that, before, what people do, before directly going to the prototype, they analyze those things in on the model. And then if you know things about model, then what you expect that the same things to get accelerated at what, prototype. So how to find out the relationship between that? Let us say that there is something, let us say that u of the model is this one, then what will be the u of prototype? So how to do those analysis? Okay, so tangential velocity of wheel, first thing is u is equal to pi dn by 60, this we know. So u is proportional to dn, this we know. Okay. And u is proportional to v, this we also know. And v is proportional to the square root of h, this we also know. So can I say that square root of h is directly proportional to dn? So from this one, square root of h upon dn is to remain what? Constant. Constant. So can I say that if I take the whole square of it, so can I say that h upon d square n square, this is to remain constant? Okay. So h upon d square n square of model, this will be equal to h upon d square n square of whom? Prototype. Okay. So how question appears in the exam? Let me tell you. How question will appear, that they will tell you that there is a model 1 is to 2, 1 is to 3, 1 is to 5, like that, and is working under these conditions, and the head is this one, n is this one, then tell me what is the head at the developed at the prototype. So if we know the relationship between these two, then we are easily able to find out that what is the head at prototype. Okay. Okay, let us solve next. Discharge. Discharge is q, right? So q, we know that q is equal to area times velocity, and for area we know that this is d square, and velocity we know that this is velocity only. Okay. And velocity is proportional to the square root of h. So can I say now that q is, and also we know now we need to eliminate h, means now what I am trying to do is that, have you seen that q, if I am talking about h, then we have only variable d and n. There is no other variable like q, there is no other variable like p included into it. Similarly, what we will do is that we will eliminate those variables like operating conditions, we will eliminate those. Okay. So now v is directly proportional to the square root of h, this we know. And we know that u is directly proportional to v, and u is directly proportional to dn. So can I say now that square root of h is directly proportional to dn? Yes. So now let us put these things into q. Let us put these things into q. So can I say now that q is directly proportional to the d square into velocity, and velocity is square root of h, and square root of h is dn. So I will replace this dn. So can I say now that q upon dqn, this is equal to some constant? Some constant. So what I can do now is that q upon dqn of model is equal to q upon dqn of what? Prototype. Fine. Similarly, let us go to power. Let us go to power. So for power, what do we know? That power is directly proportional to qh. Okay. And q just now we have seen is directly proportional to dqn, and h we have seen that square root of h is directly proportional to dn. So can I see now that power is directly proportional to the dqn and h? So can I see now that h is directly proportional to d square n square? So power is now dqn, and h is what? D square n square. So can I see that power is directly proportional to the d to the power 5 to the nq? So what I can see now is that power upon d to the power 5 nq, this is constant. Okay. So can I say that P upon d to the power 5 n cube of model is equal to P upon d to the power 5 n cube of prototype. Simple. Okay. Now specific speed. Specific speed. Specific speed is specific speed of model. This should be equal to the specific speed of prototype. Okay, specific speed of model should be equal to specific speed of prototype. So what I can do is that n root p upon h to the power 5 by 4 of model is equal to n root p upon h to the power 5 by 4 of prototype. Okay. So this is all about like turbines. So questions will mostly fall into these areas. So let us solve few questions based on this model and prototype analysis. Okay. Let me see where that question is placed. Okay. Read this question. This is appear in one of the gate exam, means in one of the year. What do I mean? So let us read this question and let us try to solve. It says that a test is conducted on a 1/5 scale. 1/5 scale model of a Francis turbine under a head of 2 meter and volumetric flow is 1 meter cube per second at 450 rpm. Then it says that the take the water density and the acceleration due to gravity as 10 to the power 3 kg per meter cube and 10 to the power 10 meter per second square respectively. Okay, no problem. It says that assume no losses both in model and prototype turbines. Then says that the power in megawatt of a full size turbine while working under a head of 30 meter is what? Got the problem? Okay. So they have given you a 1/5 model, scale model. Okay. And the model head is given, right? So hm value, I can say that this is given to us. Model head is 2 meter, and then volumetric flow is 1 meter. This is also given. Q of model is 1 meter cube per second given. And for power, this is sufficient. So power of model is rho g into qm into hm. Put these values. Rho value is given to us 10 to the power 3. G is also said to approximate as 10. and and qm is given as 1 and hm is given as 2. So what is the pm value? Means power developed at model is 20,000 watts. So this is 20 into 10 to the power 3 watt. So can I convert it into kilowatt? So pm is 20 kilowatts. Okay, one thing is done. Now, so model laws we have just now seen. So in order to what we have been said is to find out what is the power of prototype when working under the head of how much? Head of 30 meter. Okay. So now we will have to look after those conditions where head is to be find out. Okay, so head of the turbine under working head 30 mm. So power of prototype is to be find out. The head of prototype is given as 30 meter. Okay, so let us get back to the model laws. So we have seen in the power we have seen was proportional to QH. See, we can see this one, we can solve this one by sitting in the exam hall. No need to remember even. But we know, but we should know the idea how did we did this. Okay. So what we know here is that we have to keep H and eliminate Q. Why? Because H relation is given to us. And since H relation is maintained, we will have to keep H with us and we'll have to eliminate Q and we'll have to eliminate this Q in terms of whom? In terms of diameter and other things. Okay, so let us see that how do we change it. So Q is, we have seen that directly proportional to area into velocity, right? And velocity is directly proportional to the square root of h, right? So can I say that Q is directly proportional to d square into square root of h? See why I am not putting here at square root of h in d into n, because we have not been mentioned with the n, we have not been mentioned with the n, so why to carry that? So let us eliminate this. So what I can do now is that p is directly proportional to d square into square root of h, d square into square root of h into h. So can I see now that p is directly proportional to the d square into h to the power 3 by 2? Can I see that p is directly proportional to d square into h to the power 3 by 2? So can I solve this one like that p upon d square into h to the power 3 by 2 of model is equal to p upon d square into h to the power 3 by 2 of prototype. Okay. So P of model we have calculated as 20 kilowatts, right? Or let us put it into the basic units. Let us not convert it into kilowatts. So P we have seen was 20,000, right? 20,000 watts. And D we have seen, D we have no idea, but D relation we have been given. This is 1 by fifth scale, right? 1 by fifth scale. Okay. So what we need to find out the power of the prototype. So what I can do is that into multiplied by d to the power d of p upon d of m whole square. Can I write? Yes, now the prototype relation is gone into this side. So prototype is in the upper side and model is on the lower side. Similarly, h of prototype divided by h of model to the power 3 by 2. We can see. So what is now the power of prototype is 20,000 multiplied by what is d of prototype, diameter of prototype upon model. This scale we have been given. So 1/5 scale means what? That model has been reduced 1 by 5. So the prototype diameter is 5 times of diameter of model. So this dp upon dm, 1/5 scale means what? The d of prototype, d of model is what? 5. So this is 5 by 1 whole square, and h values has been also mentioned, right? So h is initially 2 meter in the model and prototype is working under 30 meter. So model head is 22 meter and sorry, prototype head is 30, prototype head is 30 and model head is 2. So 30 upon 2 divided to whole to the power 3 by 2 is the power of prototype. So can you solve this? Can we solve this one? Yeah, correct. So it has been asked into what? Megawatts. So divide it by 10 to the power 6. It's not 38, it's 375. So 380 will be also there. So divide it by 10 to the power 6. Yeah, yeah. In the model and prototype relations, you must have studied in dimensional analysis. Yeah, 29.047. Correct. So questions based on this area will appear. But again, see, how did we how did we improvise this relation? That did we remember anything? No. Just what you need to do is that read out what is given to you in the question. You know how to open this formula. Yes or no? So we knew that just now we saw in the model and prototype relation, we saw that power something like this one, p upon d to the power 5 nq. But if somebody mugs up this formula, but the question appear in another form, so there is no relation between n given, then how you will solve? You will get stuck. Yes or no? So in order to avoid those things, what you are supposed to do is that always read the question, improvise at that point. Okay. So we knew here that power is to be calculated in terms of diameter and h. Why? Because d and h relation was given. Suppose he has given uh, n values, then we could have solved with respect to that. Okay. And even if somebody puts this one now, then we know the relation between n and h. How the relation? What is the relation between h and n? Yes. So can we see that n is directly proportional to the square root of h upon n? So nq is there now. So no, d. See, I am helping you to solve the one question in using many ways. So what we can see is that here there was n, but we do have no idea that what is n given to us. We have only given d and h. So from this relation, can we see that n is a square root of h upon d? So what is nq? Nq is nothing but h to the power 3 by 2. Why? Because this is 1 by 2, whole cube is 3 by 2 dq. Put this relation here, put this relation here. So what we can see is that power is d to the power 5 and nq is h to the power 3 by 2 multiplied by dq. So this is converted into d square and this is h to the power 3 by 2. So can you see that the same thing we have done? Can you see that same thing we have done? D square into h to the power 3 by 2. Yes, simple na. Only thing which you need to mind on these things is, I'm repeatedly telling you that stick to the basic, open the formula how you can do it. That leave no unknowns, means that leave no dependency that this is dependent upon this or not. You have to reach in terms of what? Diameter and h. Okay. Let us solve one more question. Means your this part is done. I hope that you have got all those things. So let us solve this question. Can you solve this question? So now they are asking you what is happening in the model. What happens in the model? So let us solve this. So power at the model is to be find out. What is given to us in this question is that power of prototype is 300 kilowatts. Okay. And then n value of the prototype is also given, that at 1000 rpm. Given na, that a large hydraulic turbine is to generate 300 kilowatt at 1000 rpm under a head of 40 meter. So h of the prototype is also given as 40 meter. Okay. Then it says that testing is under 1 is to 4 scale, okay, of the turbine. And what is the head of the model is 10 meter. 10 meter. Then it says the power generated by the model. So power generated by model is what? Simple now. Just now we have seen this problem, just now. The same thing you analyze here and tell me the answer. Tell me what is the answer. Please solve. You should try to solve few questions sitting in the classroom also. Tell me the value. A option. A option is 2.34. Very good. So this was just to make you appreciate the fact that the questions will not be tough. I have seen that in the previous classes you guys were feared that how questions will appear, that how to solve those things and all. So just be confident that the questions will come into these manners only. Okay. Okay, so this part is also finished. Means there's nothing much. What nothing much? There's nothing remaining from now, from my side into this one. So yeah, one more thing: the turbine classification. How did we classified it now? So there is one classification based on a specific speed, and there is one classification on working head. Okay, so one thing we know that power is rho g q and h. Okay, so what we can do, that if a turbine is high head, if the turbine is high head, then its discharge will be what? Low. Similarly, then this is which turbine? This is Pelton turbine. If the head is high and discharge is low, this is Pelton turbine. Similarly, in the case of power is rho GQH, and in the axial turbine, this is in the axial turbine, what happens is head is very low. Head is low. If head is low, then I can say that Q discharge is very high. Discharge is very high. So they might ask you question that axial flow turbine is high head, low head, high discharge, low discharge. The multiple select questions are there na? So they can ask questions in the form of this, that uh, Pelton axial turbines are what? Kaplan and propeller. Kaplan and propeller, right? So they might ask you that in a Kaplan turbine, discharge is high, discharge is low, head is high, head is low. And similarly in the Pelton and Francis turbine or the reaction turbine, this is also reaction only, but Francis is radial flow reaction turbine, this is axial flow turbine, and this is tangential flow, right? So see the name there and their classification. Okay, now working head. So working head in working head of which turbine? Pelton turbine. So this is very high, means I told you now that in the Pelton turbine the dam is to at the very high elevation compared to what, compared to the turbine level. So working head of working head of Pelton turbine. So working head of Pelton turbine will be greater than or at least equal to 300 meters. So then this falls into what, that when you are working at 300 meter or above, then you are under whom, Pelton turbine. And when you are working below 10 mm, 10 meter, less than 10 meter, your head is less than 10 meter, then you are at, okay, let me erase all these things. Based on head I am classifying, right? So let me write it very clear to you so that, see, everywhere there are different means different book codes, different kind of units. So mostly what I can say that under head classification for Pelton wheel, for Pelton wheel or what impulse turbine, the head is usually greater than 300. Okay, and I can write it here also. So for Pelton wheel, for Pelton wheel, the head, I what did I say, the head is for, yeah, screen share I have ended, I will write down here only. So for Pelton wheel, I'm trying to quote that value which is very accurate. Why? Because there is no accurate somewhere written. So somebody says something else, someone says something else. So for Pelton wheel, this is greater than 300. And for Kaplan turbine and Kaplan and propeller, right? So for Kaplan turbine, H is less than 10 meter. This we should know. These limits, if I know, then we can say that okay, if they have mentioned what is this value, then we know that where it is lying. Okay. And now let us classify based on what? based on specific speeds. So okay, so I have just attached a figure into that part. So let me show you that. Can you see something on the screen? Can you see there's a table I have attached on the screen? Yes, yes. Please note these things. So, if the turbine type is propeller or fixed blades, then the class is reaction and the head range is between 10 to 6 or even below that. And similarly, adjustable blades are called Kaplan turbine, and the head range is in between 10 to 60 meter. Similarly, if we have diagonal flow turbine, not of much importance to you now, but you should know. And if you don't remember this one, it's okay. But Francis turbine, you should know the head lies between whom 330 meter to 400 meter. Okay, but sometimes it can go up to 500 to 600 meter. But for Pelton wheel, I have told you repeatedly, this is impulse turbine and the head range is above 300 meter. Okay, and now I will tell you that what is the specific speed range. Sometimes I have seen the question appears and they will ask you that what is the range of a specific speed. Okay, so specific speed. So the specific speed table is something like this. I'm drawing the specific speed. So your specific speed table would look like when your Pelton wheel is with single jet, Pelton wheel with single jet, with single jet, then we have 8.5 to 30, 8.5 to 30, and the unit is in SI units. Okay, and when we have Pelton wheel with two or more jets, Pelton wheel with two or more jets, then we have this range 30 to 51, and then we have Francis turbine. Francis turbine, the range for this one goes from 51 to 225. And then we have Kaplan or propeller turbine. The range for this goes from 225 to 860. 225 to 860. This we should know. Sometimes they will ask you that Pelton wheel is a high specific speed turbine, low specific speed turbine. So then at least we should know that where specific speed values were high, where we achieved those values low, because mm, got the idea that sometimes they will ask you that Pelton wheel is a turbine which whose specific speed. Why? Because multiple select questions are appearing, right? So what they can ask you is that Pelton wheel is let us say that Kaplan. So Kaplan is a Kaplan in a Kaplan turbine. The questions may appear like the working head is below this and the specific speed is this. So questions can appear in the jumble of these two. So we should know three things. I have told you already about the discharge quantities. Discharge and head we talked, right? Discharge and head we talked, and then we talked about whom? The head range, and then we talked about a specific speed. So combination of this one, like in objective exams other than gate exams, like sometimes we write PSU exams, so their questions keep on appearing like this. Okay, so this I guess completes our this hydraulic machinery part. Means most of the part is covered. So pumps anyway are not in this syllabus, so they are not asking questions from pump. Sometimes if they ask questions from pump, so they priorly mention that okay, the pump is in syllabus, but here they have not mentioned, so the pump is not necessary to get covered here. Okay, so let us conclude this one also. Okay, okay, then we'll stop here. Okay, then.